Okay, so welcome to this next tutorial. So in the previous tutorial, just as a summary, we have created a very nice mesh of pipe, and it was very simple to make it. Some couple of highlights include whether you uh, add volume in your physical groups or not. Otherwise, you will face error while importing the mesh in openFoam. Second thing is you need to take care of the zero folder because if the names mismatch, then there is a high chances of crash of the paraform. So with this, now let's move ahead with the next agenda for this tutorial, and it is tutorial 4 with the learning objective of running the simulation. So we are back with the simulation. So we'll start our very first simulation in this case by our own self. So initially for the testing we have used cavity and Pete's daily maybe, and from that we have learned many things, some many introductory things. Now this is formally our first simulation wherein we'll be learning key things, minimum key things to learn to run a simulation. So let's get started with this. So the objective are to set the boundary and initial conditions, set up physical properties, and solve and type parameters, and then run the simulations. You should be familiar with the Hagen-Poiseuille flow and basic fluid dynamics concept, and you should be familiar with the creation of 3D pipe geometry in openFoam. In the previous tutorial, we are done with this point. So this is the problem setup. Okay. So you're having the walls here, you have parabolic velocity profile in the steady state. This is the inlet, this is the inlet velocity, this is the outlet. The dynamic viscosity is this, and so the kinematic viscosity is this. So essentially, the fluid turns out to be water because of these numbers. Geometry check. So as far as the geometry is concerned, so you are having this U average D and then kinematic viscosity, which turns out to be 250, and hence the flow is laminar. The boundaries assumed somewhere around 2000 to 2100. Okay, before this thing you are having everything as laminar essentially. The transition goes around from 2000 to 4000 or 2100 to 4000, and then beyond 4000 you are assumed perfectly to be in the turbulent region. That's the idea. Next thing is calculate the entrance length. So this is the entrance length and everything, 0.15 meters. So what is the entrance length? Let's see in the geometry, right? Let's see at the end of the simulations. Solver detail. So we'll be using icofoam here is a transient solver for the incompressible laminar flow for the nutrient fluids. Simple definition. Suitable solver for Hagen-Poiseuille flow. And now let's get started with the pressure boundary condition. In the previous tutorial, what we have done is this thing. I'll just go here, delete it. Yeah. Home pipe. Here we have imported this thing, and we were able to visualize in Ubuntu. So parafoam, close it and then apply it. Yeah, very colorful looking. Let's make it common looking and then surface with edges. This was the geometry. You can visualize it using parafoam also. If you want to if you want to see many lines, many building lines at the same time. So this is how it looks like. Now our mesh is ready and it has been accepted by openFoam without any errors. Believe me, this is a very good achievement. If openFoam is accepting your mesh, yeah. Otherwise, there have been a huge struggle in the computational fluid dynamics where people have dedicated their many hours to decode the problem and are giving many hours to decode the problem. So the mesh is now imported. You have got this polymesh updated. Yeah, they have seen for every mesh import you are having polymesh, and for existing polymesh the polymesh is overwritten. Okay, there is no like polymesh one, polymesh two, polymesh three. No such thing. Only this is accepted. Now boundary. In the boundary we are having names like inlet, wall, and outlet. Only three names. So what is said by the zero folder? Let's have a cross check on that. Now I'm going to rename it as original zero. F2. I'll just name it as 0 now. So now 0 folder comes in game with the paraview directly. Do we have a name mismatch? Let's open P and U both at the same time. Enter. Do they open? Okay, one by one then. So you're having dimensions like this: internal field, wing wall, fixed wall, and front and back. What is this? Is it pipe geometry or what? It says moving wall, front, fixed wall, and front and back. Okay, no problem. We'll edit it. It is not a very big deal. So what is given here? It says at inlet you are having zero gradient, outlet fixed pressure, wall at zero gradient. Okay. So let's edit these things here. Sorry, for pressure, right? So what it says, for the pressure boundary condition, you need to have boundary field में you are having this as inlet. I have name as inlet. So this is in accordance with the polymesh boundary file. Okay. Boundary file located in the polymesh subdirectory. So at inlet you are having this as zero gradient. At outlet you will be having as fixed pressure. This F should be small. Need to look at this, and wall is at zero gradient. Zero gradient is already written, so I will just what I will do is I will just target it as wall. Okay, and then here is the outlet. Here is the outlet. Outlet me you are having this fixed pressure. So type. So there is something called as fixed value. I will just write fixed value. Sorry, value being zero. Value being zero. Let me check from the other tutorials if this is rightly written. Okay. So I know where the tutorials are located. Also, you please pay attention. So it is OPT openFoam 7. So we have been copying tutorials from here only, right? And then let's say you are having incompressible, and then icofoam you are having. There is no pipe tutorial. Simple foam, laminar. Let's say anything. Block channel or planar Poiseuille flow. 0 U, not U but P. Notepad. You are having the walls boundary condition. Okay, so it is an advanced kind of boundary. Pink cone cylinder. What is there at the outlet that we need to check? Far field moving zero gradient. Sorry, here it is not there. Block channel 0 U P. Outlet there is this fixed value, and then there is this internal field. Because the value of the internal field is uniform 0, we can use this directly. So I've just copied it and I will just paste it here. Okay, so it will take the value of this variable as internal field, where internal field has uniform 0 value. So I think this pressure condition is okay. Now I'm back in the velocity now. So what is there in the velocity? I'll just go. Oh my god, why did it close that? Not new folder, but I need to go in it. New window. So you, right? And in this u, we need to have what? Let's see. We need to have a velocity of 0.025 meter per second, right? So let's write it here 0.025. Okay, this is the velocity for what? Inlet. Okay, this is at wall and this is at outlet. I mean, wall should be at no slip, and then outlet velocity will play as velocity will play as a role of zero gradient, right? At the end, there should not be any kind of gradient, so that condition is there. So let's cross verify. Just tutorials and then incompressible, then icofoam, cavity, not cavity, so let's say pimple foam, laminar, block channel, 0 u, notepad, open it. So at the outlet you are having this velocity as zero gradient. So let's just copy it and shall I just write it here? Okay, at outlet you should be having this as this thing zero gradient. So now I think the system is now well defined. Let's check it once with this. So we have defined the velocity. We are okay with the dimensions. We have checked our mesh. The pressure at the exit is 0 pascals, open to the atmosphere, and parabolic velocity profile we are supposed to get as per theory. Okay, let's check this kinematic viscosity wala part. So for this, again, sorry, I have been navigating again and again. Please don't get confused. Pipe, constant, transfer properties. What is it? So it is written as 0.01 here. So I will write as 1 e power minus 6 because this is what is mentioned there, right? 1 e power minus 6. So what are we currently doing? We have copied the cavity case from tutorial to our run directory and renamed it simultaneously as pipe. So this command no here, where is that? Oops. In the tutorial 3 it was there or what? Yes, in the tutorial 3 it was there. In this the meaning of this command is you are copying into foam tutorial. You are copying in the run directory from foam tutorials this cavity folder and you are naming it as pipe simultaneously. So this is the meaning of this command. Now we are back here and okay, so this is done. Now you calculate the Reynolds number and with the machine dimension or the pipe dimensions and the flow velocity it comes out to be 250 and hence it should be laminar. Accordingly, the entrance length comes out to be 0.15 meters. And to and to understand the full development of the flow, we should have a pipe length more than this, which is a perfectly okay case for us because we are having the length of 0.3 meters. Okay. Next is solver detail. We'll be using icofoam. Let's check if we are using icofoam. System control it. We are using icofoam. Okay. Next is pressure boundary condition we are having given velocity boundary condition checked. Okay. It says no slip boundary condition 0 meter per second velocity. Now I think we are good to go with the simulations. Let's open the terminal, then ls. So where there are zero constant system, you are ready to run. So mesh is already imported. So no block mesh, nothing. Only one thing we can do is check mesh to understand the various parameters inside the mesh, whether they are not negative volume or something like that. There are many determinate kind of things are also there. So use check mesh. It should come okay. So this comes as mesh okay, and you are good to go with the simulations because you have checked the imported mesh. Now it's time to run the simulation of icofoam. It is taking a lot of time because the mesh we have generated it is very what I would say Very, very fine. Really, really fine. So here, no, here there is this current number. This current number, no, it's increasing, meaning the solution is getting diverging eventually. If this happens, then there is a high chance that our simulation will not succeed. So then we need to optimize our mesh accordingly, right? So initially it was 0.17 or something. Now it is really, really high. Please have a look. It is 0.16 here, and then at the, where is it? 0.174. So it is gradually increasing. Let's see if it crashes or not. And one more thing to highlight here is you are having this huge number of iterations. These are very, very huge, 285, 286, you know. So these are kind of indications that your simulation is having very, very low chance of success. And every time it is taking the same. And the current number is gradually increasing and not coming in place. So solution is diverging. We just close it. Need to terminate the simulation in between somehow. Now we need to optimize the mesh again. How should we do that? Open the mesh again. Open. What we need to open? Channel or pipe. Let's open pipe. What we have done in the mesh, geometry, edit script. So let's use with some lower number. Instead of 20, let's have 10 only. Or we're having initially 10, right? And here we can have 100. In case your simulation support, in case your machine supports this, you please go ahead with the higher number of mesh. But then because it is taking a lot of time to simulate here in my computer, I am just making it fairly simple. This we have done previously. So the mesh may look quite rarely defined in the surface, but yeah, it is more towards, we are approaching the pipe geometry. So let's mesh 3D. Yeah, okay. Reload the script. I didn't reload the script. Yeah, I'm really sorry. Now it is fine. File, export 3D MSH. The size should be less now because we have removed the additional points. Version 2. Okay, closing it. Then we are having downloads, MSH file, Control C. Let's go in our cold folder, which is this. Paste it here. Please note the size. This is 10 MBs, and this is, sorry, replace the file in destination, and this is 1.2 MBs. See the reduction in the size now. F5, and we are ready to import the mesh again. So what we have done currently is we have optimized the mesh so that the simulation happens faster. And then we have exported the mesh from the Gmesh, and now we are ready to import it in openFoam. So let's import it again. GMSH to foam, GMSH to foam, file 3d.msh. Mesh is imported. Now because the mesh is imported, there will be a new polymesh will be created, and that we need to, you know we need to edit all of these kind of things. So inlet should be patch, wall should be wall. Alright, and then outlet should be patched. So let's close it off. We don't need to edit zero folder because we have already defined the PND one. There will be no further change in this because the mesh import normally causes the change in constant folder and not zero and constant system collectively. So I think these both two guys are fine. Constant transfer properties, not bad. This is also fine. I'll just check boundary also. Okay. I think we can directly run the simulation. Let's go. Before that, check mesh charges in to check the mesh, which is okay. And then maybe icofoam run. Now the simulation is running quite fast. Okay, it has converged. Not actually converged for this case because it is a transient kind of thing. So we have given it as zero point 0.5 and it has gone to 7. The previous simulation with the higher number of grid points would have come to zero point 0.5, but then the Courant number was increasing, right? Courant number was increasing, and uh, it is not like it was so. The significant rise can be can be considered. There may be some slight variations with the Courant number that can be ignored, but then essentially it should be very small. Now our simulation has come to an end. So let's go to parafoam, capital F. It should open now. Now let's close it, apply it. Let's plot it. Let's plot a U here, and at the end, okay, this is the velocity variation. How much time is this in the recording? I don't know if I can check. The recording is 22 minutes. Okay, so I will just we'll just visualize it in the next tutorial then. Thank you so much for your patience attendance, and please let me know for any further doubts. Yeah? Thank you so much. We'll continue in the next tutorial. Thanks. So just to summarize, we have ran our first simulation. We have created a mesh using Gmesh. We have imported it. We have exported, and then we have imported it in the openFoam. It is a 3D pipe geometry, not a 2D one. And so the simulation ran with some initial boundary condition. We have used the cavity as a initial reference case, and using that we have been running. Okay, after simulation, what is it that we need to check? Okay, the simulation is ran. This is a success. Next is what? Let's discuss in the upcoming tutorial. Thank you so much.